So as you guys know, I'm having surgery this week, and as a result, I'm recording this class. This is the class for, I believe, the seventh. I can't even remember. I'm sorry. Um, but I'm going to double check the date. It's either the seventh or 11th. It's the seventh. Um, so it's software testing. It's going to enter a new area of software engineering. This particular area is kind of particularly important to me. Most of my research as a academic professional has been in software testing in some way or another. Um, I've authored about eight, maybe 6 to 8 papers in this area. Um, Pretty cool area to be in. But software testing is one that we talk about a lot, but nobody really gets involved. It's a little bit more. This is not code heavy. So very unfortunately, a lot of students think that the easiest job, they talk about this, is the easiest job to get as a um, graduate of computer science is really in software. Um, they say it's in, web development. It's actually not. And although there's always a need for software developers in that area, full stack web development, the actual easiest job, one of the easier jobs to get into is actually quality assurance. The level of code that you need to actually write is actually relatively minimal. It's similar to data science in that regard, but it is unfortunately not as high paying, right? So you have that aspect of it, but it is a relatively easier area to break into. Um, but anyway, we're going to talk about testing. And testing largely follows a lot of things. So don't assume it's just one thing. It's actually a lot of things. Testing is the idea. One of the things I want to think about, what I want you to think about from a testing perspective, at least in this class initially, is testing is not just verifying a program does something specific, right? Don't assume that, right? We'll talk about that specifically, but think of computer science being a science, right? You observe, you experiment, you test a hypothesis, right? You see if the experiment worked. That test is testing, right? And understanding that process is key to being a good developer as well as a good tester, right? So it's really important to understand that as well. So we'll talk about that quite a bit, but the idea is that with computer science is you're observing something, you're making a hypothesis, then you're experimenting, and then you're testing the hypothesis, so to speak. You're seeing if what you did worked. Okay. Okay. That is a more general term. And why that is important is pretty simple. No matter what kind of testing we're looking at, that definition fits better. Okay, we'll talk about that as well. So we'll talk about program testing, the two core types of testing, and what are we trying to accomplish with each. Then we'll talk about validation versus verification. We often talk about validation and verification together, but they are separate, totally separate things. We'll talk about code inspections. Wait till you get to your first job as a developer and you're doing code inspection. Everybody sitting around a table looking at your code and making comments. And then you draw down the comments and you go fix your code. Yay. Pretty basic, right? But that's a code inspection. We'll talk more about that as we go along. But we can do code inspection from a variety of perspectives. That is a true corporate code inspection type process where we have a tricky bit of code and we're going to review it. It's, a particular area that's causing us no end of hassle because there's something that seems to constantly be going wrong in this area. And so we're going to do a big code inspection. But, code inspection also could be 2 or 3 people looking at code just to see if it's doing what it's supposed to do. Most often, we talk about this, it's an underrated aspect of computer science. So one of the things, if you've ever gone to see a tutor, the very first thing your tutor does is ask for your homework, and then he looks over your code. One of the best ways a tutor can do his or her job, is to look at what you've done and identify what you've actually done, right? Not relation to the homework, what your program is actually doing. Most of the time, it's obvious where the error is once he or she just identifies what's your program is actually doing it. Usually it's very, very obvious. And that's via code inspection, believe it or not. That is that same process. It's just in the small, like it's just you and some other person as opposed to a group. And then we'll talk about testing processes. Testing processes are usually code execution. We'll talk about that. It's not always code execution. We can do some automatic testing tools that can look for specific things. But we'll talk about that as we go along. And then we're going to talk about the stages of testing today and provide detail of the activities and purpose of the testing performed at each of these stages. So testing is intended to show that a program does what it's intended to do and discover program defects before it's put into use. Okay. All right. As you can clearly see, that is two different tasks in one sentence. Testing is designed to show that a program does what it is supposed to do. Yes, so to speak, it meets requirements, but it also is intended to show errors before we go to production. So essentially, we're testing to see if the program does what it's not supposed to do. Okay, pretty simple. When you test software, you usually execute a program using artificial data. You give it fake data, check the results, boom, is the results of what you expect. You check the results of the test run for errors, anomalies, or information about the program's non-functional attributes. So when we have non-functional requirements, such as response time, those type of things we talked about, that's when we do the test program where we're actually providing, our test harness might actually have, what's the word? Might actually have, metadata recordings so that we can determine the response time and stuff like that. So we're not just checking the results, we're checking how long the results took to make. We can easily reveal the presence of errors, but you can never identify that errors are not there. And you go, what do you mean? So you can only find errors that you test for. Pretty simple. It's a very, very simple idea. But you can only find errors that you're looking for. Okay? If you're not looking for an error, that doesn't mean it's not there. It just means you can't find it. You can't reveal the things and so forth. Now, having said that, we refer to this as the test cases generally show failure, not the possibility of failure, right? So you can definitely see situations in which a test might not actually perform, where it executes the code and it reveals certain types of failures, but doesn't reveal others. And if you don't test for that specific thing or that specific problem, it doesn't find it. Think about virus protection as an example. Virus protection works very, very well, but it reveals the presence of viruses that it knows to look for. Yes? Imagine you're looking for the cold, you're looking for COVID, you're looking for, I don't know, chlamydia, right? As an example. So you test for each one of those things. But those three tests alone cannot show that you don't have pneumonia, as an example, right? That's not how it works, right? You have to actually be testing for that pneumonia to determine if you have it or not. And that's the general idea here. Test suites, test cases only show the errors they're looking for. So you may just not have an adequate test suite to identify actual problems. We'll talk about that in more detail later on as well. Testing is part of a more general verification and validation process, which also includes what we refer to as static validation techniques. Static validation techniques are not dynamic, since they're static, but dynamic. When we think of program testing almost to a person, you're all thinking everything we have to do is run a program to see if it works the way we expect it to work. That's actually dynamic. We're executing a program using artificial data and then checking the results. That's dynamic testing. There are some static validation techniques which we can use to verify correctness. So we'll talk about that as well. Testing goals. Right? We talked about two particular situations. One, we're going to demonstrate to everyone that the software meets its requirements. We're going to identify that the software, the program, does what it's supposed to do. Right? You have a set of requirements. Does it meet those requirements? Done. That is quite literally goal A, right? And it sounds silly, but it's true. You have a set of requirements. Do you meet all the requirements? Done. For custom software, you should have at least one test for every requirement. For generic software products, there should be tests for all the system features plus combinations of features that will be incorporated. We'll talk more about test coverage in a later date, but the general idea is if you have a requirement, it's supposed to do X, then you should test to see if it does X, right? Ta-da! This is the notion that you're testing the program to see that it operates normally and correctly according to its requirements. The second testing goal is to cover situations when behavior is incorrect, undesirable, or does not conform to a specification. Okay, this is different. So now we're looking for defects. Okay, system crashes, unwanted interactions with other system, incorrect computations, data corruption, whatever. If we execute with incorrect data, we should get a certain outcome, right? But our programs should be robust and deal with certain types of situations. So we want to discover situations in which the behavior is incorrect. So we're actually looking for it to fail. And we want to make sure it doesn't fail, or it doesn't fail in a bad way or whatever. It fails according to how we want it to fail, as an example. And that's what defect testing is about, right? We're testing this program to see if it does what it's not supposed to do. Okay? Pretty simple. The first goal leads to what we refer to as validation testing. So we refer to it as validation testing fairly simply because if you have good requirements, then you have the system performing correctly, reflecting the system's expected use. Hence, you're validating the system. Okay? The second goal leads to what we refer to as defect testing. The test cases are designed to expose defects. The test cases in defect testing can be deliberately obscure and need not at all reflect how the system is normally used. Suppose someone enters in 100 instead of 10. Well, that's incorrect. It's well out of range. What does the system do? It shouldn't crash. It just should report an error, right? This is what we refer to as defect testing, right? It doesn't have to be similar to the way in which a program would actually be run. Validation testing looks a lot like acceptance testing, and because part of it is, but the second goal, defect testing, is more about making sure the program is not going to blow up. When a user gets it, not sure what to do with it, and enters in incorrect data or what have you, we want to make sure the system's not going to crash. So we end up with validation testing and defect testing as our primary testing goals. Obviously, validation tests meets requirements, so a successful test shows that it operates as intended. Defect testing is different. We discover faults or defects where the behavior is incorrect or not in conformance with the specification. Doesn't meet specification, in an edge case, it doesn't perform like it's supposed to. A successful test is a test that makes the system perform incorrectly and therefore exposes a defect. These two things are not congruent. For validation to tests to be successful, that means it meets the requirements, right? Therefore, the test should pass, essentially. The test goal passes. Defect testing, a successful test is one that makes the system perform incorrectly and so exposes a defect. This is one where the intention or the goal is to produce test cases that fail, right? So they don't necessarily go together. Their goals are different. One of the things we see frequently is software developers frequently use validation testing as their primary means of identifying our requirements are being met, Software testers or quality assurance people are using defect testing to take a bit of software and throw some things at it to see what happens. And they're looking for defects. We rarely have these being part of the same test suite. Okay. However, every now and again in the development life cycle, suppose Alice she's doing validation testing and she finds a defect. The system doesn't perform as intended. Well, she might make a defect test to make sure that that defect does not appear in the future, right? So even though she's doing other things, she might have a situation in which She's going to write a defect test to make sure that, hey, that problem we occurred, we don't want that problem to happen again. So we're going to actually make a test to see if that problem's occurring, as an example. So that does actually imply, but we're written differently. With developers, generally, we're looking for things to pass. With defect testing, we're looking for things to fail. We're looking for problems. So we're always trying to get test cases to fail. Slightly different goals, both intended to make the system more complete. Validation testing obviously is we need that before we can sign off on it, but defect testing also helps us make more robust software. So model of the program testing is you have input test data and you have output test results. Some of those output test results are going to cause the defects. So what is the input test data that would cause the defects? That's usually the problem, right? It's not enough to know that the defect occurred. You need to know when the defect occurred and in what situation. And so the inputs and the situation that lead to the anomalous behavior is very important to record that part in a test case. So test cases by themselves, when you think about what a test case is a set of inputs, the state of the system, and an expected output, right? So the expected output, if the expected output is not received, so we need to know what the actual output is. And then we can compare the expected and actual not being the same reveals a defect. Verification versus validation. We'll talk about this again. Are we building the product correctly? Sorry, apologize. Right? This is specification. We have a specification. Are we meeting the specification? 100%. There's no variation here. That's exactly what it means. Okay. Verification is 100% taking the requirements and fulfilling the requirements. Validation answers a different question, but it's fairly similar. Are we actually building the right product? At this point in the system, you actually have a system to test, is the general idea. So you have the user, and you can have them test it out to determine if the software does what the user really, really wanted it to do. Remember, the user and you went together toe to toe and you built some requirements, and hopefully you built the requirements very well, and they're very good requirements and all those things and da 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 da, right? Great. That's the overall goal, right? But when you actually build the software, the customer gets to look at it and says, well, what if we did this? And right, you run into those problems. So that's validation, and that's a separate animal, and that requires the customer. We can do verification because we have the requirements. We can verify that the requirements are met or not met, but we cannot do validation, okay, by ourselves. We need that customer to do that. And the reason is the customer needs to be shown the software to determine if it meets the actual goal. Almost 100% of our discussion today will be on verification. We talked about validation and meeting validation via prototypes and other things in the requirements discussion phase. So we're going to assume that we have good requirements going forward, but that's your general verification process, right? We're going to be focusing mostly on verification. Validation, showing the customer what you have and is this really what you wanted? Is part of this process, but it's more requirements gathering. We talked about it already, so we're not going to spend a whole lot of time on it. The aim of validation and verification is to establish confidence that the system is fit for purpose. It is going to be signed off on. It depends obviously on the system's purpose, user expectations, and market environment. So software purpose, the level of confidence depends on how critical the software is to an organization. We need to make sure the software does what it's expected to do. But also, if it's very, very critical to the organization, then that software better do 100% of what it's supposed to do, exactly as it's supposed to do. Whereas if it's, less critical, right? That's where the level of confidence comes in, right? It's not a guarantee. It's not you have to do this or what you call it. The level of confidence changes. User expectations, of course, users may have low expectations of certain kind of software. So a lot of people ask me, so Michael, how come Microsoft was just a giant bug a million years ago? Microsoft Word was just buggy, and there was a time in which they had one feature that was hard coded to be 12, font size 12. things like that. And the answer is really simple. When computers were relatively new, people did not have high expectations of bug-free programs, right? People used Excel more often than they used the other tools because it did the things they wanted to do with the little amount of work that they had to do. Did it do everything perfectly? No. In fact, people still make fun of, you know, moving an image on a screen in Word causes all sorts of problems, right? But you have a level of users have a typical level of expectation for certain types of software. Sometimes we expect them to be bug free. We expect them to work very easily. We don't expect a whole lot of XYZ, right? And so that has its variation. And that's why Microsoft did so well with Word, Excel, and so forth. It was easy to install. It did all the things that people need to do, right? And they made it really simple to have it all at once kind of thing. But yeah, initially early on, people didn't expect high level of functionality, right? It expected to be buggy every now and again. But the reality is now the expectation is very, very high. These things they got to do exactly what we want them to do. And so forth. But anyway, go back. Marketing environment. Getting a product to market early may be more important than finding defects. If you want to get it to market early, maybe we cut a few corners and don't find all the defects. We get to market early. Yes, it has some bugs, but hey, it does what it does before anybody else does what it does, right? And maybe that's some variation that makes verification less important. We'll make sure it meets the product requirements, but maybe we won't make sure that it's free of very, very free of defects. All right. So software inspections. This is concerned with analysis of the static system representation to discover problems. You go, wait, what? We'll talk about this in more detail, but this hopefully you've already done. Yes? And you go, what do you mean you've already done it? You have your program, your homework, your whatever the hell you're doing, and you reviewed it to see what it does. Or you've asked someone else to review it, and they look it over, talk themselves through it, and identify what's actually happening in the software. That is a low-level software inspection. There are actual tools that we can use to document and do some code analysis and do some other stuff to help us do a more in-depth one. But the other set of eyes, right? Another set of eyes is very, very critical. And you go, why is that? Well, you may have written a paper some point in your life. I like to use this particular example. You wrote a paper in your life. You wrote it, you know what it says, then you go to read it. In your mind, you know what it says. So even though it doesn't actually say what you think it says, your brain connects those two. Okay. When a second set of eyes are looking at it, they don't know what the expectation is supposed to be. So they're just looking at the code that's actually there. And as a result of the code being actually there, they're looking to see what it actually does, not what you think it's supposed to do. And so that's why it's so important. We all run into this problem. This is not, because I'm a professor and I'm super smart. No, we all run into this problem. It's all the same thing. When I review code that I've written, the very first thing I do is try to shut my mind down to what it actually is supposed to do. Yes? Because I'm so worried about making it do what it's supposed to do, I'm not necessarily reading it for what it's actually doing, and that's 100% of the problem. So I'm trying to reduce that, but I can't. My brains don't work that way. Yes, it's supposed to do this, so that's why, right? But another set of eyes don't have that problem, right? Immediately. We'll discuss this more in another chapter. I don't know if we do it in another chapter. I don't know if we go into that much detail. I think we might, but I don't recall. Software testing, though, is concerned with exercising and observing product behavior. This is what we refer to as dynamic verification. The system is executed with test data. Its operational behavior is observed. Pretty simple, okay? Test case, we have to know what the inputs are. We have to know what the system situation is. Then we have to have an expected output and an actual output. We compare the expected output with the actual output. Is it what we expect? If it is not what we expect, we have test failure. If it is what we expect, we have test passing. Note, Tests don't pass. This isn't a test like a class. This is either pass or fail. One way to think about test passing or fail is think about thumbs up and thumbs down. We don't have thumbs to the side, right? There's no degree of failure. We just fail. There is a requirement that has to be met. It has to be either pass or fail. To just, I know that sounds silly, but it's very important. It'll make a lot of the discussions a lot simpler. Okay. Inspections and testings, we can do inspections at the requirement specifications, right? Requirement specifications, we can absolutely should be verifying that the software, that the requirements are verifiable, as an example. Do they make sense? Do they do this? Do they do that? Software architecture, we can inspect the software architecture. Is it going to meet the requirements and so forth? Can do that. UML models, that all can be expected. That is why inspections are actually so important. At any point, we can ask other developers to look at what we're doing, UML models, database schemas, or the program, and do inspections. Where can we do testing? We can only do actual testing, the dynamic verification. You can only do software testing, the dynamic verification once we have a program. Okay? If we don't have a program, we can't do testing. So that's why inspections are very, very much more important than you think they are. And they actually take place on a regular basis, right? They're very, very important to make sure you're getting them in a reasonable fashion. Okay. Software inspections involve people examining the source representation with the aim of discovering some problems. Anomalies are, edge cases. If you think about that, I mean, anomalies became very common when you talk about Star Trek as an example. Very common. It's one of the anomalies I remember. But anomaly is something weird happening. Okay. Might happen only once in a while, but it's something weird that can happen. And the defect is something happening that it should never happen. Not all anomalies are defects. Anomaly just indicates that something weird is happening. That could be just this, how that works. Who knows? But inspections do not require execution of a system, so therefore can be used at any point in the process. We can, like I said, we can inspect UML design models. We can go over them, have another set of eyes go over them to see if we're going to reach expectations and so forth. They can apply to any representation of the system, requirements, design, configuration, test data. We can actually look and see if our test cases are actually doing what they're actually supposed to be doing. And you go, wait, what? What do you mean test cases? Remember, a test is looking for something, right? Looking to meet a requirement. Is this requirement being met? Is that test case actually being met? For example, so many of you said you want the dealer to deal cards. How can you verify that that the dealer dealt the cards? Does everybody have a set of cards or complete set of cards in their hands at the end of the dealing? That's a way of verifying that dealing did occur. Yes? Ta-da! Pretty simple, right? They've been shown as a very, very effective technique for discovering program errors. This is a very common thing to do. Sometimes we do it in the small, and sometimes we do it in the large. In large, you have a large group of people going over sections of code that a few people wrote around a table as an example, usually once a week, once a month, whenever it has to happen. That's what we think of as in the large. Small is to say, hey, Bill. Well, we don't have any bills. You're right. Yeah, we don't. Hey, Bill, can you look at this for me? And Bill's going to look at it and determine whether or not that problem, what your software actually does and is it actually what you're supposed to be doing. Very, very important to do because it's very good process for discovering program errors. And you go, why? Because it works. It works really well. It works so well. Most of the time, all the other person has to do is identify what the code is actually doing as opposed to looking for a specific type of error. They just go over what the code is doing and they explain it to the developer what the code is actually doing. And most of the time, developer has an immediate, wait a second, it's supposed to be doing, and boom, we have to fix the program, right? Usually pretty simple. It works very, very well. Advantages. During tests, errors can be masked other errors. So you might have an error somewhere, and then another error is hiding. You have this big fault and this other error that you don't see because this big fault is occurring, is also occurring. Pretty common. Because inspection is a static process, you don't have to be concerned with interactions between errors, so forth. Incomplete versions of the system can be inspected without any additional cost. It costs nothing. You just have to be able to review it. You have to be able to present it in some fashion to another person for their review. If the program is incomplete, then you need to develop specialized test harness or test the parts that are available. Okay. So when we are trying to dynamically test incomplete versions of a system, we have to figure out a way to make a program run to test that part of the system. So we have to make something dynamic. So we may have to create a specialized test harness just for that part. Or we may have to have a test harness that just tests that part that's available. Who knows? Lots of individual things, but it does cost extra money to do. As well as searching for program defects, an inspection can easily consider broader quality attributes, such as compliance with standards, portability, and maintainability. You're like, wait, what? Because our ability to multitask, humans have the ability to multitask in ways that, it might not be obvious, right? And so we can review things like quality of the program. We can review things, the compliance with some standards that you might have. We can look at it in terms of portability. We can do all these things at once because we're reviewing the code. We're reading it as we go along, and we can make some judgments about all of these types of things while we're doing a code inspection, which is quite huge, right? It's hard to discuss portability and maintainability without a code inspection, by the way. There's some things that are just harder to well, it's very hard to automate, as an example. So certain types of things with compliance with certain types of standards and so forth might actually be difficult. It's easy to do in a code inspection. Inspections and testing are complementary and not opposing. Just because you do code inspections does not mean you don't need to test. Both should be used. Inspections check conformance with specification, but not conformance with the customer's real requirements. Inspections cannot check non-functional characteristics at all. No non-functional characteristics can be checked whatsoever in the inspection process, which is very, very important. Also, when we talk about customers' real requirements, remember validation testing is the notion that it actually does what the user actually wants to do. That's dynamic testing. They're looking at what it's actually doing and seeing if that meets what they actually want to happen. There's no way to do that statically. We can verify things, but we can't validate things in the inspection process. So a model, how do we do this? We design test cases. A test case is not necessarily the executable body. Very important to note this. So we refer to as a test harness as something that executes a test case. And you're like, wait, what? So we'll talk about this in a little bit. What is a test case? Right? For the most part, a test case is usually some form of identification, identifying what you're going to test, usually a set of inputs, the state of the system, if you need to know the state of the system, and then expected output. And that's your test case. Then you're going to prepare the test data, get the test data together, get the inputs ready. Then you're going to run the program with the test data, and you're going to get the test results. At that point, you're going to compare the results to the test cases. And then you're going to produce a report. The test cases are either going to match what's in your test case, right? In other words, your expected output matches the actual output. If that happens, that test passes. If it doesn't happen, it fails. We will see some unit testing when we, go later in the class. So we'll see you guys. We'll use the JUnit tool within I think NetBeans just to show you what the testing process looks like. It's a very simple thing, but we can create pretty simple tests using JUnit as an example. We'll create some tests and produce some reports, but basic idea. Stages of testing. So, one more thing. When we talk about test cases, we will actually talk about this in more detail later on. But test cases are not necessarily executable programs that just take your test data and produce inputs and so forth. Test cases are categorization of data, right? So this is what we're trying to test, the purpose of the test, some identification thing, set of inputs and a set of outputs, and what we call expected outputs, and we're going to compare the expected outputs later on to see if it passes. Okay? Ta-da! That is your test case process. And we do that for all of our test cases, and so forth. That is the testing process. Pretty simple. So we'll talk a little bit more about what's in a test case and so forth later on, but let's talk about the stages of testing first. Development testing is where the system is testing during the development to discover bugs and defects. There are lots of different ways of doing this. You can use test-driven development where you're actually building tests before you actually develop the software. And that means as you're developing the software, you can determine if it meets or doesn't meet a certain set of tests, a certain set of requirements as you're actually developing it, right? Or you just run a set of test cases while you're developing. They call this desk testing as well, because you're on the developer's desk. The same person programming is usually testing in this regard. We're making sure it does what we expect it to do. Typically, although not 100% of the time, it really depends on what the developer is actually doing in order to test the system, right? Like, it really important. If they're working on a simple object, they test that simple object. If they're working on something bigger, they have to test that as well. It depends on what you're actually doing to build the test. Release testing is where you release it to a team. A separate testing team may test a more complete version of the system before it's released to users. Release testing is a very different animal. This is usually almost always a separate team, and they're going to be looking for defects. Of course, they're going to actually take the requirements of the software and they're going to turn those into tests, obviously, right? Completely separate from the development team that may have done their own testing to create the set of requirements. They're going to do it separately. And the reason for that is they want to build an acceptance, a list, they want to build a set of acceptance tests. Yes. While the development team is actually building the software, the release testing team or the quality assurance team might be building a set of test suites to test the requirements. In the process, they're also likely creating defect tests as well. So when we release it, when the development team says, hey, we're finished, the release testing team actually gets the software and runs it through its paces. If there are problems, obviously, guess what? It sends it back to the development for testing or fixing, bug fixes. User testing is a different animal. User testing is where users or potential users of a system would test the system in their own environment. So we think of release testing as the formal acceptance process. User testing is more like what we think of as beta testing. Okay, it's much more simple idea of what we think of user testing. Now, we'll go into these in more detail. As you might have guessed, development testing is not that simple. Development testing, as we integrate more and more components, we have to do more and more integration. We have to do more and more things. And as a result, that is not as simple as just development testing. There are stages of development testing, as an example. User testing, like beta testing, those type of things are very, very important in certain environments. So we'll talk about that process in detail as well. And the release testing is pretty simple given the other types of testing. Okay, it's just done differently, right? When you're development testing, you're often building test cases as you're developing. And once the test case is developed, why would you get rid of it? You keep it around, you keep running it, and so forth. Release testing, on the other hand, you build a complete set of tests based on the requirements. You don't get the data, you don't get the software, you get the requirements, and then you build a set of test cases to say, hey, we're going to meet the requirements this way, right? With release testing, when we're doing defects, you can't look at the software to determine what kind of defects. You look at likely types of things that could occur, those type of things. So it's a different way of doing it. We're going to talk about black box and white box. Black box is more like release testing. They don't actually have the software to look at to tell it where things might go wrong. They're just basing the things on the requirement, and the system essentially is a black box. We can't look inside it to see what's doing. hence the word black box. And so that's why we're going to refer to that as release testing. Development testing is almost all white box. And that just means the light's on inside the box, and you can see what's inside the box to determine what's the best way to attack this software, and so forth. User testing is a whole other environment. You're actually giving it to some certain select group of users to see if they like it, if they don't, if it produces problems, and so forth. We're going to talk about alpha, beta, and so forth, the types of tests. I'm going to make jokes about Microsoft. I'm going to make jokes about lots of um, programs. There have been a lot of failures in this regard over the years, the well-known failures, and we'll talk quite a bit about that as we go along. But that is another set of testing that occurs. I personally have not been involved in anything beyond development testing, but my research is focused on development testing. But like I said, beta testing and alpha testing and so forth are actually quite interesting areas and quite right for research later on for those graduate students in class. But it is kind of interesting on its own because it does actually, it is 100% dynamic testing, but it's actually testing in the wild, so to speak. You're actually putting the system through its paces by giving it to a user who's going to do whatever the heck they feel with it, right? We see this a lot in games because I'm a gamer, and so I play games a lot, and so I frequently have played games and so forth, and as a result, you know, we're going to make jokes about testing, but the point is that, games are buggy, right? And sometimes they're released with bugs in them. I wish I had kept it. I didn't keep it even when I was a kid. But I had a gold box Zelda game, original Zelda, that came in the gold cartridge, which was really cool. Um, but mine had a bug in it. And that bug in it would, prevented me from completing the game. For this particular version of the game, there was a helpline a million years ago, a Nintendo tip line. And then I called them on the tip line saying, like, I think I know what to do, but he won't let me do it. And so the person on the phone walked me through it. And sure enough, and he told me, well, it's buggy, so you can return it, blah blah blah. And so I returned it, but I wish I'd have kept it because apparently it's worth a lot of money. So if I'd have kept it, apparently it was one in a million, not one in a million, but one in like, you know, one in 100,000 or something like that, that got produced, that had that defect, which would make it worth more money. But anyway, but that's what we refer to as user testing. People are going to actually do what they're supposed to be doing. Remember, we can't count on users to do what they're supposed to do. Just as an example, and this is a very simple example, those of you who've played Mario, um, the most deadly character in Mario is in fact the Goomba, and it's the very first Goomba that appears in Super Mario, the original game, and that's simply because people were learning to jump and didn't know they couldn't run into the Goomba. And that's kind of how user testing goes. We don't know what they're going to do with the system when they get it. So who knows? But it is actually interesting. So we do go through it in this class, and so forth. All right, so we discussed program testing and the two main types of testing and their goals. Remember, we're testing to see if the program does what it's supposed to do, and we test the program to make sure it's not doing something it's not supposed to do. Very important. We talked about validation and verification. We talked about what level of confidence needs to be provided in certain situations. We're going to talk about this in more detail. There is no such thing as providing 100%. There's no way to ensure there are no bugs. It's not possible. Not at all. So, well, I mean, we will talk about this later, but the basic dilemma is we can only test for things we're looking for. If we don't know we're supposed to be looking for something, we're probably not testing for that particular defect, and that's how that makes it into production. But like I said, anyway, we talked about validation and verification. We talked about the different types of things that it tries to do. Then we talked about code inspections versus static testing versus dynamic testing, essentially. The code inspection is the primary static test tool. And then we think about testing processes and dynamic actually executing a process. And then we talked about how a testing process actually goes through. That process that I showed you, you develop test cases, and you develop a test harness that takes the data and turns it into executable code, then actually runs it. We'll talk more detail about that because that is somewhat accurate because I'm really kind of high level doing it because sometimes it is very simply you take a test case, a set of inputs, and you provide it to the input of a program and it produces output and you just check the output. So most of the time it's just, hey, we need to take these inputs to this program. And so we're just passing inputs to a program. Sometimes it's that simple. Sometimes we have to get the program to be at a certain state and then we execute the code. So there's a whole bunch of things that go into that. We'll talk more about that later. Um, but that's the testing process. We also talked about the stages of testing, the three basic core things. We talked about user testing, acceptance testing, which we refer to as release testing in this book. And we also talked about development testing. We're going to get into each one of these, but the purpose of each is different. And then we'll go into the detail of the activities as well as we go forward. All right, if you have any questions, please make sure you ask them. There is a last homework that's going to come out, but this last homework is not a doing homework. It's an evaluation homework. You're going to evaluate each other based on a rubric that I provide. At this point, you would have worked with every other student at least once or twice. And all you're going to do is report on the quality of that work. All right, y'all have a great day. Thank you. Trying to